I am Frederick Bordry. By education, I'm an electrical engineer a long time ago. I did all my career at CERN, building large experiments. I participated heavily to build LHC, 5 billion machine. I can say you can some research before and to spend, I discussed during the break, to spend in a clever way 5 billion, you need time. People claiming they will spend that in the next 3, 4, 5 years. Good luck for the procurement and so on to do that in a clear, important things. I'm Gauss Fusion CTO now, and to reproduce Diego, our keywords are Stellarator. I'm in line with Carlos saying the Stellarator will be the commercialization machine. We are engineering company with a folder engineering company. I think we are looking the engineering how to build and not to build only the first of a kind, but how to build a series of fusion power plant. To go to very close, very small reactor, Stellarator is not our goal. It's to be a global optimization and to look at how we can operate and can maintain for 40 years the things. Okay, it's not the topic of today. The topic of today, is to look at superconducting magnets, cryogenics, power converters. I add power converters, but I think this is a global thing, the optimization between superconducting magnets, cryogenics, and power converters. What I did in the previous role as the director for accelerator at CERN, where I built LHC. But before looking at the future development and what could be the spillover, let's look back, because I think we can learn a lot of history and what is the synergy between all the domains. I think the superconducting magnet development comes from high energy physics. The first large apparatus, the large machine, is the Tevatron in Fermilab, Chicago. And Robert Wilson, the father, said that Tevatron was the grandfather of all the superconducting projects. I think this is true. This Tevatron was, 80s, was put in the 3rd of July 83, I remember very well, put in operation. And Fermilab was 4.4 Tesla magnet with niobium titanium. I think it was really a good thing with 100 tons of niobium titanium. This was a push. And immediately this created a lot of spillover towards especially medical application, MRI and NMR. I will come back to that. In parallel to that, it was starting fusion. I remember Torsupra, now called West. They were starting, and there was also with niobium titanium, but it was an innovation. Innovation was in cryogenics, superfluid helium. Instead to stay in helium at 4K, to go to 1.9, 1.8 with superfluid helium. It was a success. And thanks to the success, we decided at LHC to use superfluid helium in saving and increasing the energy of LHC. And I think also after Tevatron and this breakthrough at Torsupra, it was in parallel SSC in US, LHC in Europe. Unfortunately, for very political reason, all reason, SSC was cancelled in '93. LHC was continuing. It was a success. It was put in operation in 2010. 2 years after that, discovery of Higgs boson. And it was mainly also an accelerator with niobium titanium. It was at the beginning thinking, could we go to niobium-13? But we thought at the time that niobium-13 as a LTS was not mature, and we take a look at all the supply chain, all the things, and we decide to go to niobium titanium. I think it's always a message also, be careful you want to build something, not to look at maybe the extra last things when you have a laboratory. Very good to have very emerging technology in the laboratory, but if you want to build in the next 5 to 10 years an apparatus, maybe you have to use existing technology. At the same time, it was a development of ITER. ITER starting development of a magnet, I will follow that, 90 to 2000. The choice obviously was to do LTS, niobium-13, because we have to go to up to 12 Tesla, 13 Tesla, then it was obvious to go that. And I can see that ITER pushed the market of niobium-13. It was more than 500 tons needed for ITER with several manufacturers, 7 years of procurement, supply chain. Don't forget the time you have for the supply chain. And I think this was very pushing, establishing niobium-13 as a new conductor, cable, and construction. This, I have to say, also push the domain to increase the field for MRI and NMR. And also, it was a decision at CERN to use for the upgrade of LHC niobium-13. Without ITER, we will not have used niobium-13 in LHC. And now this is I can say, is a circulus, virtuous circulus between high energy physics and fusion. And I think this, I'm convinced, it will continue in the future. I think this now in niobium-13 is also used in KSTAR, GT, SXT, SA. Then saying that, now we have the market is really niobium titanium is a mature thing with more than 1,000, 1,500 tons per year, mainly in MRI and MR. Niobium-13 LTS is more mature. We have not so much, but it's really established. And now we are discussing this morning, HTS is coming. It's a very important thing that it will have a future, but I will come back to that. What I want to say is that MRI and MR profit from the market. You know that now, for example, the market for MRI in 25 is $9 billion, and NMR is $1 billion. Projection, I've discussed with people, they are projecting to have $12 billion in 2030 for MRI and $1.3 billion for NMR. Then this is definitely this. And they are looking to go higher to 6. Already in MRI, they are using the insert with HTS, and certainly with the development HTS, they will be pleased to do that. Now, to continue, I think I'm convinced HTS is for the future, because for all the reasons we announced. I'm not convinced we will use infusion for high field. I am very in line with Gianfranco, but for high temperature. To go to high temperature, to go to 20, 30 Kelvin, will simplify the cryogenics, reduce the consumption. Maybe we compute in gas fusion for 1 gigawatt electrical, 3 gigawatt thermal from 50 megawatt to 15 megawatt, and close to 40 megawatt to reduction. I think it is more margin, but still some maturity problem, and still under radiation there is some unknown in terms of degradation with radiation, in terms of, and one of the things very important is also the supply chain. I think for me is a key thing, especially in Europe. We have no supplier. Maybe they come, they claim they will be the second worldwide provider in next year. Okay, I can only believe them, but when I saw your drawing, I have put in some question mark. We have no supplier substantial supplier in Europe. The main ones are in China, are in Japan with some Russian fund. CFS is building conductor, but from I know they are buying their things from also this China and so on. Then I think we definitely need, and this is maybe a question for the things, we will need investment in Europe to get a leader producing HTS. Without a dramatic investment, 100 million, 200 million to produce in the order of 100 kilometers per year of HTS, we will not have our supply chain. And this is, for me, is very important. I have to say that I said I will speak about cryogenics. Cryogenics is really now something mature. Thanks to all the projects, we know how to build large plant of cryogenics. Was made for ITER is ready to be operated. Unfortunately, ITER is not ready. At CERN, LHC, we built up to 100 megawatt of cryogenics. We know to that. We have good supplier. And in Air Liquide, Linde, to mention in Europe, I think they could improve. They will have to improve. Now we have improvement towards higher temperature, 20, 30 Kelvin, and maybe higher. Okay, now I have almost things. I want to say also power converters. I think power converters, ITER, for example, developed this power converter based on the old technology, Thyristor 1, with a lot of reactive power. We can go now, as everybody is doing now, with switch mode power converter with IGBTs. I think definitely is a way to go and to go in modular things. We are now looking at 100 kiloamps, a few volt power converter. We have to develop that with compensation of reactive power. This is a modular things, because when you have 100 kiloamperes, we should have modular things with reliability. You can junction some module. This could have a big spillover towards drive, to be application in transport. This, I believe, we have contact with former ABB Hitachi, and they are looking this kind of thing. Okay, I don't want to, some list was the spillover technology. Obviously, I can see medical imaging, MRI and so on, but also hadron therapy when you are building cyclotron, synchrotron, gantries, big gantries when you want to move the beam around the patient. This with superconducting, especially in HTS superconducting, will be very interesting, not to have all this liquid helium that. Maybe not once again with the field, but with the high temperature. And you mentioned all the power grid. I think the power grid is definitely the things. Transmission line, I think this will be HTS, but mainly magnesium diboride instead of REPCO. And all what it is aerospace, transport, and so on. We had contact with people doing liquid hydrogen, the same technology for cryogenics, but also maglev train and so on. I think I will not to go to repeat the sense. To finish, I think I will say, once again, the question is how to invest in HTS manufacturing to reduce the dependency of non-European suppliers and also the low number of suppliers. How to foster cross-sector R&D to share innovation between fusion, medical technology, energy, and energy physics. This is very important. We have to look at also training. We can see we are looking desperately in all the domain, new engineer and superconducting technology, and that we have to think in Europe how to form more. And obviously, I think we believe now private is important. Engineer and private should take the lead from physicists and public, but we have to create PPP, and I think this is very important, and to help SME, a small company, new company, to move from prototype to industrial development, and for that they need test of platform. We know that we have in Europe, I know now CMAT is building one, INFN, CERN, CEA in France. We are how to can share this platform to test our magnet and so on. This is an important thing. Okay, now I'm very over. Thank you very much.
Frederick, thank you so much. Thank you.